Yesterday, we finished discussing the uses of radioisotopes. These you actually already knew because they were in your definitions. Then we went back and we hit transmutation of elements. I'll let you watch the video to get these, or you can grab them from another person, but I just want to bring you to one really important difference. There are two types of what are called transmutations. Transmutations are when you change an element from one to another, and you have natural transmutations, and here's the key. You have one reactant when you have a natural transmutation turning into products, and then you have what are called artificial transmutation, and that's when you bombard the atom with a high energy particle, and you have two reactants. So in this case, you got an alpha particle hitting an aluminum atom. That is the difference between artificial and natural transmutations. So I want to talk a little bit more about those today. So under artificial transmutations, let's start right here. It says the first artificial transmutation was performed by Ernest Rutherford in 1919. Now you guys have heard that name before. What was the experiment? Very good. It was called the gold foil experiment, and it proved that the atom had two things that are really important. What were they? Mostly empty space with a positive nucleus. Perfect. Yeah, that's good job. Rutherford bombarded nitrogen gas with alpha particles to produce an unstable isotope of fluorine.
Can you zoom in a tad?
Sure.
I thought there was a U.
There is a U in fluorine. Thank you. There absolutely is a U in there.
Is it U?
F-L-O-U. There we go. Okay. What he did is he did the following. He took nitrogen 14-7 and he bombarded it with an alpha particle. He liked alpha particles because he used that in his gold foil experiment as well. And he produced fluorine 18-9.
I have a question.
Yeah.
How do you determine where the numbers go? Because I kept missing that on the Castle Learning.
When you say the numbers.
The 4 and the 2, the 14 and the 7.
Yep, the mass is always on the top, the charge is always on the bottom. The atomic number is always the bottom one, which
Okay.
also is representative of the charge,
Okay.
and the mass is always the top.
Okay.
F18 decays into actually another product, oxygen 17-8, and a proton. Don't really need to know what it decays into, but rather just the fact that this was unstable. And this experiment actually helped to discover the proton. All right. Close to that time, James Chadwick, another chemist, discovered the neutron in 1932 by another what's called transmutation experiment, where he changed the element of one atom into the element of another atom. Elements above 92 are called transuranium. Transuranium elements because they all undergo transmutations.
Wait, okay, and then our
So elements above 92 are called transuranium because they all undergo transmutations.
is it like elements above 83? Is that the
Anything above the atomic number 83 is radioactive. Yes. And none of these elements are found in nature. They must be synthesized in nuclear reactors. So they're actually made by chemists in nuclear reactors. They're not just found naturally occurring. If you notice, a lot of your upper elements of ones above 92 actually have weird names, like Am is americium. You have Einsteinium. Those names are actually the person who discovers the particle gets to name the atom. So that's where you get some of those weird names. Okay, this is the part I really want to focus on today, which is nuclear fission and nuclear fusion.
We talked about this in US.
Did
Yeah,
you?
we did.
Yeah.
Oh, I heard you guys talking about that the other day, I think with the atomic bomb or something.
Yeah.
Fission involves the splitting of a nucleus into smaller fragments, and the process begins when you have a slow-moving neutron and it strikes a uranium-235 atom. So I want to draw kind of what happens here in a nuclear fission reactor. If you have a neutron, all right, we know a neutron, the symbol for it is going to be
Isn't it O with a slash?
0, 1, and 0. This can hit then uranium-235. So it basically comes in here and it hits an atom of uranium-235. And when it does so, it produces two other atoms. The first one is an atom of krypton-91. The other is a lighter atom as well of barium-142. And then what happens is, in this, it also produces three other things, which are three more neutrons.
Is that 142?
Yep.
KR91.
KR-91.
What do the circles represent?
The atoms. Yep, I'm just trying to represent the atoms. So when this happens, a neutron hits a uranium atom, it produces two atoms and three more neutrons. Now what's crazy is that those three neutrons, those can go and now hit
Oh gosh.
more uranium atoms, and each time they hit a uranium, they produce three more neutrons.
It just keeps going.
And what it initiates is a what reaction? Yeah, this initiates what's called a chain reaction, which can be used for energy or for a bomb. So the key here is to recognize that a fission reaction always involves a chain reaction. The speed of that chain reaction is what differentiates an explosion of a bomb or controlled energy production. Okay, that's the difference. When atoms split into two smaller atoms, more neutrons are released,
Can you move it up?
which split other uranium-235
Up too
atoms,
far.
and a, thank you, chain reaction is started. To give you a little perspective about how much energy is actually created here, and I'm going to rephrase that because we don't create energy, but how much energy is essentially formed from the mass that decays. 1 kilogram of uranium that undergoes fission releases an equivalent amount of energy as 20,000 tons of dynamite. Now, a kilogram is about the size of a grapefruit, or about the mass of a grapefruit. So, the little boy, what's that? How does anyone know how big the bomb was that was dropped, the first atomic bomb? Yeah, you're right. It really wasn't that big in terms of, it was the fact that it was a nuclear explosion, so you get a lot more energy from that. I think it was about 120 kilograms. All right, which really, that's not a huge bomb in terms of like a normal explosive, but it created, think about this, guys, 1 kilogram creates 20,000 tons of dynamite. So if you have 120 kilograms, you're multiplying 20 times 120, and that's equivalent to the amount of dynamite. So it's really, really powerful. For this, the equation that you don't need to know, but just so that you're understanding where the energy is coming from, Einstein showed that mass can get converted into energy in a nuclear reaction. And so that's where the energy comes from when you have nuclear fission occurring. By the way, what one takes place in, let's just add one note here. that in nuclear fission, this is where you are having this take place. This takes place in a nuclear reactor. So all nuclear reactors right now are fission reactors. Okay, so nuclear reactors right now are fission reactors.
We have an organics test.
A what?
Organic chemistry.
Test?
Didn't you pass them back already?
Okay, I'll have to get yours. I think I put it back in the box. Nuclear fusion. Little bit different than fission. The process that involves two nuclei combining to form a single nucleus is called fusion. The way I kind of keep these straight, fission breaks apart, fusion puts together. So if you undergo fission, you take one heavy atom and break it into two lighter ones. When you undergo fusion, you take two lighter ones and combine it into, you're fusing it into one. Fusion releases a tremendous amount of energy, even compared to fission reactions. But fusion reactions require temperatures greater than basically 40 million degrees Celsius to occur. High temperatures are needed in order to give the positively charged nuclei enough energy to overcome electrostatic repulsion. Does anyone see a problem with 40 million degrees?
Hot. How hot is the sun?
Excellent. You can't have a material that can withstand that temperature. One of the biggest problems to getting nuclear fission to work on Earth, because this is what happens on the sun, that's how the sun produces energy, it's through nuclear fusion, is that everything melts. So you have to contain your fusion reaction in what's called a non-material medium, which we're going to talk about. You can't contain it in any material thing. Fusion has not been sustainable on Earth. At this point, they've not had it become truly sustainable. They've done very short amounts of it, but it hasn't been truly
I
sustainable.
want to get sick.
How do you have material that's not?
I'm going to talk about that. Hold on just a moment. We'll get that with problems. The sun provides energy by using fusion reactions. Here's how it works. You basically end up combining on the sun hydrogen atoms.
Those ones are dashes.
Ones to produce helium and a whole lot of energy. So on the sun, you have a fusion reaction of hydrogen atoms. You put hydrogen atoms together to form helium. And that's what actually creates the incredible energy of the sun. 657 tons of hydrogen are converted to 653 tons of helium every second on the sun. That's incredible. Why do you have a 4-ton mass difference?
Because it goes up by 4. The mass.
Mass is converted to energy. You are taking some of your mass and you're converting it to energy, and that energy is what sustains life on Earth in terms of our energy supply. Scientists are studying how to control fusion reactions. The problems are all materials melt at such high temperatures. So scientists are trying to find the reaction in a non-material container such as magnetic fields. So, Hannah, have you ever seen someone levitate an object with a magnet? So essentially, if you surround your nuclear reaction with multiple magnetic fields, you can essentially create a region of space that is bounded. It's basically like saying you're taking a magnet underneath another magnet, making it levitate. It stays in that position. So you can surround it, and magnetic fields don't break down with heat. So you can actually create a non-material fence that doesn't melt.
Wouldn't it be hard to make that particle?
Stay there.
Yeah.
Oh yeah.
Wouldn't it propel?
It's very hard. You're right. And that's where this research is coming into play, is how to get these to work. The other idea is to use lasers to create the fence, because light doesn't break down with heat as well. So to try to keep them, but that is part of the major problems right now with making fusion work. Containing the reaction in an area with something that doesn't melt it. Magnetic field could produce magnetic forces on charged particles and keep the reaction confined. Second option, aim lasers at the common point and drop solid pellets composed of frozen hydrogen isotopes through that point, and also try to use the lasers to keep then it confined. Scientists have succeeded in making fusion reactions, but the energy input is still greater than the energy output, so they're not getting useful energy production as of yet. But it is considered the holy grail of energy, because the main fuel for fusion is hydrogen. Hydrogen is the most abundant element on Earth. So if we can figure out how to get energy from fusion, there's a couple of huge issues. Here's what they are. The first one, you can never have it go out of control, meaning you won't have a nuclear meltdown.
We can't see.
Yep, thanks. Number two, you don't produce air pollution in the form of greenhouse gases, because you do produce helium, but that's non-reactive, and it's not a greenhouse gas. So that's a really good thing. You get a byproduct that's basically non-toxic. The byproducts also are non-radioactive, and that's very different than what's found in a nuclear reactor, where everything that is produced in a nuclear reactor are radioactive. The fuel for fusion is hydrogen, which is the most abundant element on Earth, and so essentially we're not going to run out of it, which is pretty awesome.
If somebody did figure that out, would they be obligated to, they would be able to own it or anything, right?
Yeah, good question. They could probably get some sort of a patent on the method to do this. So it's a really good question. Most of the places working on this they're not individuals. They are universities and firms that are governmentally funded. So in all likelihood, the information in that case would be disseminated. It's not like it's a moneymaker. But
Would you really only need it to work one time?
no, you'd have to have it sustainable.
Well,
So
I know that, but you would only.
yeah, if you could find how. Yep. Good question. You would probably still need more than one, because just like in any reactor, you generally are still producing electricity through the use of spinning turbines that then, and it basically is a generator, and then the energy has to get transported from power utilities and down power lines. You lose energy over great distances, so you probably would need multiple fusion plants around the country. Nuclear reactors. I want to just do the first part of this. Approximately 21% of electrical energy in the United States is generated by nuclear reactors. The reactors use fission. And what is fission? Is it what's done on the sun or what's done in the atomic bomb? Definitely not on the sun. Fission, you break apart. They produce energy needed they produce energy which is added to water to produce, I don't know what I was trying to say here.
None of that sentence makes sense.
It's to produce steam.
To produce energy needed to water to produce.
This is
heat
a really
to heat
poor
water.
sentence. I agree.
So
I think it's the heat water. Yep.
Do we exit out?
But here's what I do want you to be aware of.
Oh gosh.
What you're using the energy for here is in all nuclear, well actually most power plants basically take the energy of coal, if it's a coal burning power plant, and they heat water to turn it into steam, and that's what powers turbines.
Is there any big coal plants down in PA?
A lot in the Ohio Valley, so on the western PA border. Yep. One of the things that nuclear reactors do is they replace the coal with nuclear fuel so that you don't have the dependence on fossil fuels. 1 kilogram of uranium fuels produce more energy than 30 freight car loads of coal. So the downsides, so I want to just kind of break this down here on our own here. The negative sides is that you produce nuclear reactive waste. Is uranium what? It is essentially non-renewable because it is a resource that is limited. There's a finite amount of it on the Earth.
What is that?
So it's not considered a renewable
Yeah,
resource.
what is that lie that I do for?
I'm just separating it from here.
Oh.
So nuclear waste is produced. You have security concerns because they become terror targets.
They become what?
Terror targets. So if someone wanted to basically drop a bomb on a nuclear reaction plant, they then create a radioactive explosion rather than just an explosion. So they do become, you have to be aware of security issues.
Is that terror target?
Terror targets, yep. There have been, as we've talked about, some accidents that are not related to terror that have happened. So you have to be aware of that. You also, however, have some positives. First of all, nuclear reactors produce no greenhouse gases. What does that help us do? Limit global warming. They also don't use fossil fuels, which is a good thing. Also, a lot of times related to global warming, but we know that fossil fuels are getting rapidly consumed as well. And they are efficient, meaning that once the initial cost for setup is done, they are very efficient forms of energy. They also, as much as we fear the nuclear accidents, they have a good safety record. There's been very few nuclear explosions in the course of nuclear energy history. So there's a lot of safety systems put into check. Okay, that's what you need to know for tomorrow. One thing that I want to do now is I want you to do a sheet on radioactive decay that we never got to. And so I'm just going to give you a chance to do this. This one's not online. I printed one out. Yeah. Good question. Yep. The helium is very light, so it basically just disperses in the air. It's not enough. That's a really good question. I mean, if it ever did, you wouldn't have to worry about it because you'd be dead because it would displace the oxygen to the point where you couldn't breathe.
Are we turning this in?
Guess what? I already printed this out.
Where'd you find it?
On the internet?
It's not the same one.
Oh,
I was
you
gonna
got
say
it.
I don't think this was on the internet. So
Wait, is it the
you
same one?
printed it out. I don't know where you got it from.
Yeah,
It's
it's
the
the
same
same
one.
exact one.
Okay. Okay, the reason we're doing this one is just to give you some practice here with half-life. So